Aerojet presents A3L, an impressive new propellant currently being developed for advanced launch systems, under contract with the Propulsion Directorate of Phillips Laboratory at Edwards Air Force Base, and sponsored by the Strategic Defense Initiative Organization Innovative Science and Technology Office. A3L, a clean, solid solution-style propellant that's easy to make and has superior mechanical properties and safety characteristics, with the potential to meet a variety of applications. Here, A3L is prepared on a small scale. There are 3 ingredients. 2 are solids and 1 is liquid. The liquid is an energetic inorganic nitrate oxidizer, and the solids are aluminum powder and binder particles. They are simply blended together to form the finished propellant. The total mix time is very short. A polymeric binder is added to hold the propellant together. No chemical cure is required, and the whole operation is done at ambient temperature. The cast viscosity is quite low and tailorable. It can be adjusted to achieve virtually any viscosity desired for the purpose of casting different configurations. Pot life can be tailored to meet system requirements for a wide variety of applications. When casting is complete, the propellant is set out to cure. Again, no chemical reaction is involved. The propellant in this example has been formulated so that within 8 hours at ambient temperature, it has cured sufficiently to be removed from the mold and worked with. The material has good integrity at this point and has developed considerable strength. When totally cured, it becomes stronger and quite rubbery. Crucial to the ease of preparation is the physical plastisol-type cure, which does not involve chemical reactions. The A3L cure system will be viewed under a microscope at about 60 times magnification. A drop of liquid oxidizer is mixed with polymer powder. A measurement scale is provided to show the polymer particle size. The large scale is 0.1 millimeters, and the small scale is 0.01 millimeters. The time-lapsed photographs show the rapid penetration of the liquid oxidizer into the polymer, resulting in a relatively uniform matrix in approximately 1 hour. Using polarized light, the stress-induced refraction patterns characteristic of a polymer cured between 2 glass plates is clearly visible. These observations are consistent with the plastisol-type cure so well characterized for polyvinyl chloride polymers and double-base propellant systems. Scale-up of A3L propellant to the 1-pound mix size is also accomplished by a direct and simple process. As in the laboratory procedure, the 3 basic ingredients are blended together. In this case, the mixer is representative of production equipment with mechanical stirring and vacuum mix capability. After the ambient mixing operation is complete, the finished propellant is cast into sample configurations, cured at room temperature, and stored for future testing. This A3L formulation has been adjusted to achieve a cast viscosity comparable to conventional composite propellants. Further scale-up of A3L propellant to the 200-pound mix size is accomplished in a standard 30-gallon glass-lined Fodler reactor. After the reactor is inspected and sealed, the liquid oxidizer is added under vacuum. The polymer powder is added and mixed to form a uniform blend. The aluminum is added in a similar manner, and the 3 components are mixed under vacuum at room temperature to form the A3L propellant. When mixing is complete, the finished propellant is cast into 70-pound Bates motors using standard vacuum cast hardware. The motors are cured at ambient temperature and stored for future test firing. Aerojet's A3L propellant possesses excellent mechanical properties, even when compared to a state-of-the-art Class 1.3 low-hazard HTPB propellant. This can be illustrated with the use of a standard Janif Instron bar. The bar of conventional HTPB propellant is elongated by the Instron tester until it breaks. This elongation is good and quite typical of current composite propellants. Compare that to the A3L propellant, which achieves considerably greater elongation. Green tape on the gray ruler at the back marks the break point of the conventional propellant. A3L is very tough, and the tensile value associated with this elongation is approximately 200 pounds per square inch. As you can see, the A3L propellant greatly surpasses the green marker. In addition to high elongation, the propellant has extremely good elasticity. To demonstrate this, the Instron bar is removed from the cure mold and strained to approximately 150% elongation. The original bar has a standard gauge length of 2.7 inches. This particular bar has been elongated an additional 4.05 inches. It is removed and compared to the original bar length. It has virtually rebounded to its original position. A3L has excellent resistance to hazardous accidental ignition. An ignition chamber is used to test vulnerability to sympathetic burning. Again, to compare, a strip of the low-hazard conventional propellant is used. It is elevated by phenolic blocks under either side. The igniter propellant strip, also conventional HTPB, is initiated by electrical discharge. Fire surrounds the propellant. High-speed photography is used in order to lengthen the apparent burn time so that the event can be seen more clearly. The conventional propellant lifts off as it ignites and generates sufficient gas to elevate it above the phenolic blocks. There is no question that it has ignited. Now, a comparable test is done with A3L propellant. A strip of the conventional propellant burns underneath the A3L, attempting to ignite it. As the flame progresses, the outline of the block of A3L is visible on top. Contrary to what happened with the conventional propellant, there is no ignition of A3L taking place. Except for some charring, the propellant remains relatively unscathed. A spark test is used to further demonstrate resistance to chance ignition. The low-hazard conventional propellant is readily ignited by the spark. It burns and is totally consumed. The A3L propellant, on the other hand, is difficult to ignite under such conditions, underscoring the fire safety characteristics of this particular propellant. A3L also demonstrates dramatic resistance to accidental ignition in the presence of burning jet fuel type kerosene. To compare, a 2-inch cube of the low-hazard conventional propellant is placed on a bed of kerosene-soaked sawdust. The kerosene is then ignited by electrical discharge. Almost immediately, the kerosene fire ignites the conventional propellant. The propellant burns vigorously to completion. However, under the same conditions, the A3L propellant resists ignition for over 3 minutes, even though it is continuously engulfed by the burning kerosene. In the field, this critical safety margin could provide necessary time for area evacuation or other emergency procedures. Note that even when the A3L propellant finally ignites, it burns much slower and less vigorously than the conventional propellant. It does, however, burn satisfactorily under motor conditions. With chamber pressures in the range of 500 to 1500 psi, it burns quite readily. Resistance to breakup on impact and shock is demonstrated with a shotgun test. A dark plug of the low-hazard conventional propellant travels from the shotgun to the impact area. You can see the bright flash, followed by debris bouncing back from the target area. Note the broken propellant fragments. Now the same test using A3L propellant. In this case, the velocity of the plug is more than 100 feet per second faster. Impact produces a significantly less intense flash. Note the absence of debris. The A3L propellant rebounds virtually intact. Keep in mind that the conventional HTPB propellant used in these comparisons is certainly one of the best propellants in production today. So the superior characteristics of Aerojet's A3L really demonstrate an exciting new direction in propellant technology. And A3L is environmentally attractive. The current propellant formulation produces no hydrochloric acid and no sodium chloride salt in the exhaust. There is no degradation in specific impulse performance from the propellant used for the current Space Shuttle solid rocket motor, and processing costs are potentially lower. In addition, equipment cleanup is accomplished with water. The liquid oxidizer and polymer binder are biodegradable for minimum pollution risk. Finally, performance. 2 firings of a 70-pound Bates motor yielded predicted thrust time behavior, demonstrating that A3L burns in a controlled manner. A3L's greatest strength may lie in its wide-ranging potential. It already shows great promise for use in large space boosters, and Aerojet is evaluating how the solid solution technology approach may be applied to insensitive minimum smoke propellants. The feasibility demonstration of non-metallized A3L formulations as insensitive minimum smoke propellants is already well underway. The successful testing of 2 3KS-1000 motors containing approximately 7 pounds each of A3L propellant show great promise for A3L in this important technology area. A3L, one of Aerojet's exciting new technologies for a changing world.